I've promised to be brief. The CfA Colloquium is, in my view, one of the most important, if not the most important, regular items on the CfA Colloquium, to the point where when it's entered into my calendar, I never record who's actually going to speak on any particular week, because the only reason I could look at that information is to decide not to go, because the default is always that I'm going to go. But in spite of myself, I've known who's going to give today's talk. I've been looking forward to it for a period of time. And it's the inauguration of the Zoom version of the CfA Colloquium. So this is a significant, unexpected transition for us. But at this point, I'll hand the floor back to you, Randall, with thanks for organizing an extraordinary series with a great start.
Thanks very much. And then I will hand it over to Belinda, who will be our host today, and will introduce our speaker. Thanks, Belinda.
Good afternoon. So, as I was just introduced, I don't need to say, but I will. My name is Belinda Wilkes. I'm currently the director of the Chandra X-ray Center at CfA. But as announced on Monday, I will be handing over the baton to my successor, Pat Slane, on the 28th of September, so just a few more weeks. It is my great pleasure today to introduce one of the giants of X-ray astronomy, Professor Andy Fabian of the University of Cambridge. That is the original Cambridge in the UK, the one that actually does have a river Cam with multiple bridges across it. To welcome Andy as our first remote colloquium speaker of the new academic year. Apparently, I have this honor because I was the first person to propose him as a speaker, following his award of the 2020 Kavli Prize in Astrophysics. It is now 9 p.m. in the UK, and since I am currently in Cambridge, UK, visiting IOA, still remotely, including X-ray group coffee times, which are great fun, I will be yawning, though somehow I doubt that Andy will be doing so. I have known at least of Andy for a long time, since I was a PhD student at IOA in the early 80s. Andy was already well known in the X-ray community and led a burgeoning X-ray group. At that time, I was working on optical spectroscopy of high redshift quasars and had little direct interaction with him. But those were the days of the many CfA purple preprints. Some of you younger people may not even know what a preprint was, but they reported Einstein results, a very exciting time for X-ray astronomy, of which we were all aware. Since moving to X-ray astronomy in the mid-80s, I have become very aware of Andy's work and his place in X-ray astronomy and astronomy in general. Plus, on several occasions, I have experienced his gracious hospitality as an IOA visitor, arranging lunch groups, pub visits, and ensuring that I was able to meet and interact with his group. As a Royal Society research professor hosted by IOA for more than 30 years, Andy has led fundamental and groundbreaking research across a wide variety of topics in X-ray astronomy and on a wide range of scales. Clusters, with Perseus being his longtime favorite, multiple aspects of AGN, X-ray binaries, and too many more to cover in this brief introduction. He defines the word prolific with more than 1,240 refereed papers, according to ABS, an average of more than 40 per year for the past 20 years, and over 80,000 citations to his papers. Along the way, he has literally populated the world with X-ray astronomers as his students and postdocs continue their careers. They often dominate the speaker list at X-ray and other meetings. While he has been involved from the planning stages with most X-ray missions, for example, as an interdisciplinary scientist on Chandra's Science Working Group, and on the science study team for ESA's next large X-ray mission, Athena, my impression has always been that he spent his time on science rather than hardware. However, it turns out I was wrong. As those who have read the autobiography associated with his Kavli Prize will know, Andy's PhD, which was at MSSL at the University College London, involved building instruments and flying rockets, initially seeking structure in the cosmic X-ray background, which he found to be very smooth, requiring more than 2 million sources over the whole sky. Also, prior to that, as a teenager, he ground a 6-inch mirror and built a Newtonian telescope to explore the night skies. He clearly has skills that many of us in the field today lack. I have always known Andy to be an excellent and engaging speaker, bringing his often complex topics to any audience in a clear and straightforward way that is uncommon in my experience. So without further ado, I will hand you over to our speaker today, Professor Andy Fabian, recipient of the 2020 Kavli Prize in Astrophysics for his, and I quote, groundbreaking research in the field of observational X-ray astronomy, covering a wide range of topics from gas flows in clusters of galaxies to supermassive black holes at the heart of galaxies. His topic today, Into the Heart of the AGN, IRAS 13224-3809. Andy.
Thank you, Belinda. I'm hoping by the end of this talk that many of you will think of IRAS 13224, as I'll call it, as a really interesting object. What I want to do is to take you into the heart of this object, and if it's going to work, here we go. This is a press release image, which is also animated and gives a real impression as to what's going on, although it's actually factually wrong in all sorts of ways that I won't go into now. But it at least conveys one of the issues about IRAS 13224, and that is it's highly variable. And the heart of the AGN I'm taking to be the inner 10 gravitational radii around the black hole. And what I want to do is to show you what's going on down there. The work I'm going to talk about has involved a lot of people, and in fact, part of it is from a 1.5 megasecond XMM large project, or very large project, we got accepted, and it took place in 2016. So I just mentioned Michael Parker, Will Alston, Jiachen Zhang, Chiro Pinto, Chris Reynolds, Javier Garcia, Thomas Dowser, Erin Carra, and there are several other people. So what I want to do is to tell you about this and how we understand things about it and how it works. Now, to start off with IRAS 13224, it first became clear to X-ray astronomers it was an important object through the ROSAT survey, not eROSITA, ROSAT, back in the 90s. And there was a paper by Thomas Boller in '93, which highlighted this object as being very interesting. It's a narrow line Seyfert 1. This is an optical spectrum taken back in 1993, and you can see the H alpha and H beta, and you can see they're very narrow. Also, you can see either side of the oxygen 3 and H beta lines, a little scruff in the plot, and that is the iron 2 lines, which are characteristic, strong iron 2 is characteristic of narrow line Seyfert 1. So these are the permitted lines from the AGN, which are actually very narrow. It's radio quiet, only 5 millijanskis at 1.5 gigahertz, and it's at redshift 0.0667. Now, it was a paper he did in '97 that showed that this was a very important object. This is Boller et al. '97. I was a co-author on this paper, and what we see here is a month-long light curve using the ROSAT HRI, where they're little snapshots taken of this extremely variable object, and you see how it jumps up and down. Bear in mind that the count rate is per 1,000 seconds. This is not such a colossal count rate. It's sort of 0.1 counts per second is typical, but you can see throughout the month, it's jumping all over the place. And going from down the bottom here to up the top there is a factor of 70. So just during this month, it's showing a range of a factor of 70, which I believe is unusual for AGN. And I would say that this is possibly the most variable AGN, where what we're doing is looking not at a jet or any other phenomenon, it's the most persistently variable AGN in the sky that we know about. I'm hoping also that somebody will then challenge me in the questions. This is showing the light curve of our 2016, 1.5 megaseconds of this. And this is from a paper by Will Alston. And these are 20-second binning, 20-second bins. And each of these dashed lines is indicating different orbits in the XMM. Okay, and the top in blue is the 0.3 to 1.2 keV. Then below is the hard 1.2 to 10 keV. And you can see the variabilities in both. And this black or gray light curve is showing the hardness ratio, which is the ratio of the hard flux to the total flux. And what I want you to notice is, despite the enormous variability in the light curve, the hardness ratio is variable, but not very variable. Looking at this other plot, we can see more of the data, and then yet more of the data down here. You can see it's always roughly around 0.1 in hardness ratio. Now, if this rapid variability was due to absorption by cold matter, which you might imagine is around AGN, then you would expect to see color variations, distinct color variations. We barely see the sort of color variations you might associate with absorption. So it does look like we're looking down at the heart of the AGN, and this is intrinsic variability in this particular object. We can also look at it in 5 kilosecond bins, and doing that, the light curve is in this top panel. And what Will has done for the middle panel is, for each of these data points, which covers 5 kiloseconds, he can look at the light curve in those 5 kiloseconds and measure the RMS to that light curve. So what's the delta I, delta or F, if you like, of that particular patch of the light curve. So we can then get a light curve of the RMS. And what we then see, if we form the ratio of the RMS to the flux, is this is roughly constant. And this is characteristic of accreting objects. They show this RMS flux relation, which is almost like saying delta F, where that F is the flux, delta F over F is a constant. And accretion in young stars, white dwarfs, neutron stars, and accreting black holes all show a linear or linear-like RMS flux relation. This object, because we've got so much data, is actually showing something slightly subtler with a flux to the 2/3. And we're thinking that this may indicate there's more than one variability process taking place. And the fact it's doing this is also hinting at that. I'm not going to spend long on this. I just want to show you the quality of the variability and what we can do with it. Now, just in terms of what I think is going on in this object, there's undoubtedly a black hole. And then we'll think there's an accretion disk because it's powered, we think, by accretion. So there's an accretion disk because there's angular momentum in anything it's going to accrete, and that's going to cause a disk. And everybody's familiar with accretion disks around black holes. But there's also a hard X-ray source which is irradiating this disk. I'll talk about that in a minute. And that hard X-ray source is probably due to what we call the corona, which is emission, which is on axis in our picture here that we call the lamppost model, where it's like a lamppost above the black hole along the spin axis of it. And this cloud of hot electrons is taking the soft photons from the disk and upscattering them to make a power law of X-ray emission. They will be like almost a billion degree temperature electrons. And we think all of this is powered by magnetic fields from the disk. So the disk itself has got a lot of magnetic fields coming out of it, and they get knotted up on the axis. And that is what's causing the corona. So this is now tipping it round to show a very schematic of this. So we've got the black hole, the accretion disk, and the corona in this lamppost configuration. And this radiation comes to us directly, this power law of emission, but the hot electron corona is also irradiating the accretion disk. Now, this is crucial for the fact that when you irradiate the accretion disk and you get this emission back, it comes back in what we call a reflection spectrum. Okay, it doesn't obey the laws of reflection you learned at school. It's just backscattered emission and fluorescent emission from the disk. And it's got atomic lines in it. And having atomic lines coming from very close to the black hole means we can start to study the geometry, the velocities, and that kind of thing, the gravitational redshifts. But because we've got a powerful source of radiation above the disk, it's actually not going to be a very cool surface to the disk, or it's going to be highly ionized, in particular by the irradiation. The disk is being irradiated by this power law of X-ray emission. And in work started with the late Randy Ross in 1993, and then we published this plot and a grid of these models back in 2005, and it's been followed by work by Javier Garcia in the last 10 years. And what we can see here is the kind of spectrum that comes back from the disk. Now, this is, and many of my plots are going to have, of spectra, many of my spectral plots will have the y-axis is going to be not just flux, but flux multiplied by energy, or nu F nu, or E F E. So this is just, it tips it round so you can really see the details, plotted against the X-ray energies and optical energies down, UV energies down there. And the irradiation spectrum has got a photon index of 2, which in this particular configuration of EFE plot is just a horizontal line. So a horizontal line is going to be the irradiating spectrum, only we've got a cutoff at 300 keV, which is up here. So it's turning over down here. So let's not worry about this end of the spectrum. So it's mainly a flat irradiating spectrum that'll be just above this point here. And what happens is the X-rays that hit the disk above that peak are scattered by the disk, the electrons in the disk, but they're, because of the Compton effect, there's a large Compton recoil, and so they dump a lot of energy into the disk material. And then as you go to lower energies, there's less Compton recoil, but at the same time you start to get photoelectric absorption from, in principally, iron, which is going to give rise to the absorption edge, which is here, that absorption edge, and then there's going to be absorption by oxygen and other things down here. And when you photoionize material, the electron distribution reestablishes itself with fluorescence. And here we've got the iron K alpha line, which is at, it's about 6.5 keV. And the more you irradiate the disk, then the more ionized it becomes. And so we go from an ionization parameter, which is L over NR squared, and that'll come into the talk later on. We go from 100 to 1,000 to 10,000, and eventually you can get an almost bare spectrum of any with very few lines. The lines get broadened because the surface temperature rises and so forth as you irradiate the disk more and more. But when we have these lines, in particular, let's take the iron line, then what we've got is a line which is coming from a disk of material. If it was Newtonian geometry, then it would be a double-horned line like this, which is seen from cataclysmic variables, for example, or H1 emission from a spiral galaxy. Looks roughly like that, a double-horned line. And plotted there is what 2 different radii would give. But now we're around an accreting black hole, so the accretion disk goes up to half the speed of light at the innermost stable circular orbit. So there are relativistic effects. There's special relativity, which gives rise to beaming. So the blue wing is brighter than the red wing, and gravitational redshift, which is shifting everything further across because we're looking deep into the potential well by the black hole. And together, when you add it together in a plausible way from an accretion disk, we end up with this line profile, which is broad and skewed. And I first was working on that about 30 years ago. And this is what the line would look like from a Schwarzschild black hole. That's a non-spinning black hole. These peaks, this is sort of from the outermost radius. Now, we don't think our disks have a sharp outer radius at a few gravitational radii, so probably you don't expect to see this middle peak, but that's what it would look like if you were to just have a finite sized disk. And then as you go from a 0 spin up to a maximal spin of a maximal Kerr black hole, so we end up with a lot of gravitational redshift. So the red wing of the line, that's the left-hand side, lower energy part of the line, gets extended to lower energies. And so this means if we can measure that, how far it extends down, we're measuring the innermost radius of the accretion disk. And if we associate that with the innermost stable circular orbit around a black hole, that enables us to measure the spin of the hole. And just to point out that that has been done by many people. We ourselves have tried that. There's a very nice example from Laura Brenneman, whom you all know, published in 2009. And I was pleased to see that Chandra and Laura and her colleagues have published a nice result on the spin of, I don't know, over 1,000 black holes stacked together, 1,000 quasars stacked together to measure their, an average spin from those objects. And that was on arXiv a couple of weeks ago. So this is an ongoing, very active field. This was the first such broad line observed, and it was when the first CCD was on behind an X-ray telescope, which was ASCA, and the PI of that satellite was Yasuo Tanaka, and he led this paper that was in Nature in '95, showing this emission from the object MCG minus 63015, a bright X-ray emitting AGN, and you can see the broad line there. Now, going on to what it would look like in, say, the NuSTAR band. A NuSTAR is a hard X-ray telescope that was launched in 2012, and it looks over a band that goes from 3 keV to 78 keV, that in this sort of yellow area here. What we expect to see if we look at one of these objects with NuSTAR is, if we could just look at the reflection part of it, we would expect to see this large Compton hump, which is the higher energy bump in it. And then we've got the strong ion line, and NuSTAR does not see the soft excess. And I'll just show you some NuSTAR results, reflection in AGN with NuSTAR that Michael Parker assembled. And we can see a whole bunch of AGN where they all have roughly similar spectra. Some of them are narrow, appear narrow, sort of like this, and some of them have got narrow components like this, and some of them are just very broad and very typical. Now, the spectrum of IRAS 13224 is very broad. It's got a very broad ion line, and it looks like the coronal temperature is fairly low because this is cutting off fairly abruptly there. And notice that this data to model ratio, this is actually the data plot. What we've done is to fit the data with a power law model where the power law is anchored at 3 keV and at 10 keV. So it's been pinned down at this point and at this point. So this, we're not saying that's a property of the spectrum. We're doing that just to display the data so you can see what the shape is like, because actually the spectrum itself is very steep. If we were just to plot a photon spectrum, it would just be sort of a big diagonal line. You wouldn't see the details on it. So that's what's happened there. And Jiaqian Zhang made this plot. And if we combine the NuSTAR spectrum at the bottom with that from XMM, which is the one near the top, you can see all the details, including the soft excess in the XMM data, and the ion K, and looks like there's ion L there, which I was identifying some time back, and this is what it looks like in New Star. So IRAS 13224, not only is it remarkable for being extremely variable, it's remarkable for most of the time, it's highly reflection dominated, meaning the reflection is very strong in it. We can go to other objects, and sometimes they drop down to being very faint. And this is data that Michael Parker published in 2014 from Markarian 335, where what we see is the data here, and the fit to it requires this blue spectrum to be blurred to shift across like that. There's obviously some unblurred part here, but all of this part is highly blurred, that's highly blurred. And when we look at what's going on and try and work out where the emission is coming from, we're basically, most of this emission is coming from within 2 gravitational radii. So it's coming from very close to the black hole. We also see this kind of emission, the reflection emission from galactic sources. There's Cygnus X1 on the left, shown in hard, intermediate, and soft states. On the right, we can see at the top GRS 1915, a famous microquasar in our galaxy. And Cygnus X1 at the bottom there is actually a neutron star. That's you can see the broad line is definitely skewed. In fact, it looks like the innermost stable circular orbit is at a plausible distance to be the surface of the neutron star. And this is a beautiful spectrum made by Don Walton from V404 SIG, which flared up to become one of the brightest sources in the sky in 2015. Now, not only can we look at the spectra of these sources, we can look at the variability, and we can use the variability to measure reverberation. What I mean by that is variations in the corona will be seen directly along this line, but variations in the corona are going to irradiate the accretion disk, and there will be a time delay in the reflection spectrum because the path difference is longer. The path difference between that red one and the black one is the time lag that we're going to measure between variations seen in this path and that path. But it's complicated. Sorry, I'll come to the complication in a minute. I just want to make the point is that all the length scales I've talked about so far from spectra give us scalings in units of gravitational radii. And I'm calling a gravitational radius GM over c squared, where 2 GM over c squared is the Schwarzschild radius, is the radius of a non-spinning black hole. And a maximally spinning black hole has got a radius which is like 1.2 gravitational radii. So all of those depend upon the black hole mass. We don't actually have them in centimeters. If we want to get them in centimeters, we need to know the black hole mass in some way, which maybe we can get by looking at optical data and so forth. But if we've got time lags, we get the lengths in centimeters because we're measuring a time difference, and assuming that everything's traveling at the speed of light, we can convert that. But the observations of reverberation are complicated since we see both the direction and reflection components together. So we have to separate them out from the spectrum because they vary with energy, the different components vary, and we need spectral timing. And what I mean here, and this is just a plot from earlier work on 1H0707, which is a twin of IRAS 13224, but not as extremely variable. This is the reflection spectrum plotted there, and below 1 keV, you can see there's a big bump in the spectrum. So that emission is reflection dominated, whereas when we go between 1 and 3 keV, it's actually mainly power law dominated. So if we make a light curve in this band and compare it to a light curve in that band, we can see if there are any time lags. And we'll do that using Fourier methods. And what we need to do is then look at the lags that come out of it versus the frequency. This is that frequency along here. And what we're interested in really is not the low frequencies, which are slow variations in the light curve, And they've been known to have lags in Cygnus X1 since the late 80s. What we want is reverberation, which for these kind of objects, the narrow line Seyfert ones with masses of 10 to the 7 solar masses and less, we're looking at lag that you'd expect to be 10 to 100 seconds. This is what we saw in 1H0707 in a campaign we did back with XMM in 2008. And team member Phil Utley was the one who spotted that there was this reverberation time lag present in the data. And that time lag, we can then, being of the order of 30 seconds, we can then start to work out what the scale size is and things of this object are. I'm going to compare here from work by Erin Kara, the lag energy spectrum of 13224 in red, and that's there, and with 1H0707, which is in blue. And you see how similar they are, excepting they've got different, the red one has this axis here, and the blue one has the axis over there. But they look remarkably similar, so these lags are something which we think we are beginning to understand. And this is the ion K lag here. In other words, this stuff is coming in before that in terms of the flux. And that's, when you model it, is what you would expect. Erin looked at over 40 objects in the XMM archive and measured the ion K lags for many of them, about half of them. And she also, there they are, and these ones in pink already had published ion K lags, and compared them with the black hole mass, which was obtained from optical work, you know, the broad line widths and all that kind of thing. And from this, you can see there's quite a nice correlation. They appear to know what sort of black hole they're around. And if you just convert the lags into a scale size, then they appear to range between 1 and about 10 gravitational radii. Now, this isn't telling us instantly that this is exactly what the scale size is, because of the fact that we have both direct emission and reflected emission in our spectra. And this tends to dilute the effect. And so we have to work on that. And when we do, we find that we maybe double most of these numbers in terms of gravitational radii to convert to them as to what the path difference is. What they do, and just while I'm on this plot here, is they are emphasizing that what we're doing is looking very close to the black hole. Most of the emission is coming from within somewhere, in many of them it's coming from within 10 gravitational radii, and some of them it's coming from a bit further out, but whatever, it's within 20 gravitational radii, which is where most of the emission is coming. So we're talking about very compact sources. Now, this has been confirmed with gravitational microlensing, and I'll just briefly tell you about this, but not give you all the gory details. This work involves the Chandra Satellite, and this is, if you've got a quasar, which happens to lie behind a galaxy, which maybe is, say, midway between it and Chandra, then you'll get a schematic like this. Of course, this is not to scale. Now, strong lensing by the potential well of the galaxy leads to multiple images. And so you might get 4 images like that. There should also be another image right in the middle where it's come straight through, but you're not going to see that because of probably dust in the middle and gas and dust in the middle. So you usually see something like 4 like this. And each of those paths is going through the arms of the galaxy where there are stars. And stars in the galaxy passing through the light paths are going to cause their own lensing, so-called microlensing. And given that the Einstein radius for many of those stars is comparable to the size, apparent size of the emission region of the quasar, then this leads to very strong variability. So, what happens is these images are twinkling because of the stars passing through the different light paths. Of course, they're not going to twinkle coherently. If you see coherent variations in these, maybe with some time delay, then that's obviously associated with variability of the quasar. But the individual apparently random twinkling is due to stars and their lensing, their so-called caustics passing through the line of sight. And what that was originally proposed by Chris Kochanik back in 2004, and he and George Charters and others, and this is from a paper by George Charters from 2016, gathered this result here, where this is the half-light radius in centimeters, because they work in centimeters as well. Half-light radius of the X-ray emission corresponds to roughly 6 gravitational radii or more for these quasars. So this is independent evidence that these regions in quasars, which are in a sense randomly chosen just because they happen to lie behind a galaxy, then those objects also have compact coronae. Now, going back now, I want to get to new stuff we've got from IRAS 13224. Will Alston has been working on the lag analysis from the data, and he's used GR models by Mikhail Dovchak from Prague, and this he's got response functions of the disk for coronae of different heights, that's 6.5 and 15 gravitational radii, and you can see these response functions like this. What this means is if you have a delta function at 0 time, then you of course, and here's the sort of geometry like this, so maybe the corona is, for that orange one is down here, so this suddenly produces a flash. It takes a while for the light to get down to the disk and then out to us, whereas we see it directly like that. And that difference is going to lead to this little gap here. And then as it spreads out of the disk, we then see the response rise and fall away. If it's 15 Rg, it's going to be like that. And basically, when you look at time lags versus frequency, these translate into these curves here. Sorry about that. They translate to those curves. And what you see are 2 separate orbits from X and M, 3039 and 3043, plotted there. And you can see there's a distinct difference in the time frequency and a distinct difference in the fitted depth here. And that depth is telling us something about height, and the fact that these frequencies are changing, that's because you can see the frequencies associated with that. This has got broader frequency, longer times associated with it than this response, and that's why that is at a higher frequency. And when Will has combined that together and looked at height from all of these, he finds a height against luminosity result like that. So he's able to fit these and measure heights, which have got all the GR corrections in, and compare that with luminosity. But what's really interesting, I think, is that you can then combine all the different orbits, and they're able to correct some of the degeneracies that appear between the height and the mass of the black hole. And he's in one of these MCMC corner plots. You can then start to combine things, and you can see you get a distribution for the mass, a distribution for Rin, and for inclination and the spin. And these are the results. The spin of this object is 0.98, the inclination is 68 degrees, the innermost radius is 1.7 Rg, and the mass is 1.9 plus or minus 0.2 times 10 to the 6 solar masses. So this is 10% error on this. So we're measuring these things to 10% And some of these other quantities, that's 10%. This one, it depends on which side you're going, whether it's going, but it's high spin, no doubt. So all of these things come together. So you can make good results from this. And this was the first AGN, X-ray AGN reverberation mass measured. Now looking at the spectra of IRAS 13224 are also very interesting, not just because they have these enormous reflection features, they also show absorption features. And what you see in this plot, which is a ratio plot to a power law, so there's power law just been fitted, between there and there, and you can see the spectrum it drops below here, and it's got a big bite out of it there. And there's also, that's the 2016 data, 1.5 megaseconds, and the archival data was half a megasecond, and they also show it. So this object has got large amount of absorption. Now, this absorption line is occurring at 8.5 kV. Now, 8.5 kV, I'm not going to come up with some exotic element that's doing this. I think everybody believes that it's actually iron. And hydrogenic and helium-like lines, iron, comes from down this end of, between the hydrogenic line in rest frame is at 6.9, the helium-like line is at 6.7. So this is highly blue shifted. Now these lines, absorption lines, have been quite commonly seen in AGN, and they're called UFOs, ultra-fast outflows. They've been interpreted by Ken Pounds, Francesco Tombesi, and many others as being signatures of outflows. And these are massive outflows, because to get this sort of a level of absorption from a cloud of gas at some distance from the nucleus involves a lot of material. And the column densities to get such a deep absorption, look at that, it's a factor of a half, it drops down to a half there. It requires a lot of material traveling very fast. Here, the velocity is 0.24 c. Okay, so this is an outflow right from close to the AGN, and you end up where m dot out is comparable to the accretion flow. The energy, the power in the outflow is very large. So this is very exciting. What Michael Parker found was it's highly variable. Here's when you look at the spectrum, the high parts of the light curve, it's not there. When you look at the medium parts of the light curve, there could be something, but not very strong. And when you look at the low part, that's where all the action is. It's only observed really in the low part of the light curves, from when it's very faint. Now, you could imagine it's just because it's over-ionizing it here. So you can come up with explanations as to what's going on. And we've struggled to see exactly where it switches, and we haven't so far not actually discovered that. Whenever it's low, it's there. Whenever it's high, it's not there. And these are predicted line spectra. So here's the iron 25, 26 lines. That's the helium hydrogenic line. That's the helium-like line. And then if you saw this, you should also see other lines. These are predicted spectra. You should start to see sulfur and silicon and maybe oxygen. And we see those. First of all, Michael Parker found this by doing a principal component analysis on lots of light curves, just to try and understand what the variability was. And he found it was very bumpy, and it had peaks coinciding roughly with where these lines were expected. And this is also seen in what's called a fractional variability spectrum, which is a nice way to look at it. And that is, you take all the light curves in lots of little bins, energy bins. From those light curves, you then measure the variability of the whole light curve. And then you plot it as a spectrum. And it's clear in this plot, because it's got a false zero, that most of it has at least an 80% variability. So it really is jumping up and down. But then when you go to, say, up here, 1.5 kV and 2 kV, there's excess peak here. this is the sulfur, silicon, and so argon and so forth variability that we're seeing. So this is a way of seeing what's going on, and it appears as though these features are extremely variable. They are more variable than the continuum or the reflection by itself. Now, one thing I've been asking myself is, do these high velocities always mean outflows? Are they really outflows? I myself am excited by AGN feedback, and is AGN feedback driven by these? But one thing I've wondered about is, in an accretion disk, the orbital velocity rises to ½ c at the innermost stable circular orbit. So these velocities are always present in the orbital motions of the disk. Our line of sight passes over parts of the disk with a line of sight velocity towards us of 0.24 c. Can we make the absorber be there? Now, I've thought about this and published something about it with Luigi Gallo back in 2011 and 2013. We even fitted the spectrum of PG1211 back then and got a good fit. And this is the kind of, you can get these absorptions that are blue shifted and emission that's red shifted and so forth. But what we've done is to make a detailed model for IRAS 13224. So what I'm envisaging is there is an absorber on the disk. It's on the surface of the disk. So when the light from here comes onto there, it's going through this material and comes out there. Now, this absorber is not like a brick wall or something. It's actually material that's less dense than the accretion disk. It's therefore more highly ionized than the accretion disk, which is why it's got ion 24, 25, and 26 in it. It's got hydrogenic helium-like ion in it, whereas the disk itself doesn't, because its ionization parameter is only 10. The ionization parameter of the absorber is 10 to the 4. So that's the picture I've got in for this thing. And we made up a spectrum where we took the absorber and blurred it with the emission from the disk itself in the ways I've talked about so far, the reflection spectrum being blurred, and Jiaqian Jiang has worked that through. And here is the model. If there was no absorber on the surface of the disk, is the dashed line. And that then is, as we see it, ends up creating the black line, which, as you can see, is a fair fit to the data. And Chris Reynolds has made plots of what the thing looks like is in the low flux. This is what we expect it to look like. And notice that's 10 Rg either side of the black hole. This is characteristic sort of skew black hole. This black hole in the middle here is of course lensed, it's highly lensed. And basically what we're seeing there is the bright white part is the disk material coming towards us. The other side is the disk material going away. If we take a cut across the middle here and look at the flux, then for this low flux, it's actually extremely peaked. And most of the reflection is coming from a few gravitational radii. But in the high flux, it's actually power law dominated. So what that means is the power law is very bright. And the absorption is only in the reflection. So when it's reflection dominated, the absorption is clear. When it's power law dominated, the reflection is going to be much weaker, but it's also going to be much broader because, as you can see, the distribution of flux is much broader. And together, we see it's perfectly plausible that we don't see the emission. So that's why in this model, we can see the emission when the flux is low, see the absorption when the flux is low, but we do not see the absorption when the flux is high. What we can do here is just look in the image frame. So this is us looking at the whole thing and looking into it. And the minus 0.24 C corresponds in terms of this G factor, which is the observed over emitted energies of 1.27. So basically the line is coming from this bit here, which is close to being the very brightest part of the disk. And just something which I thought was amusing, this was from Chris Reynolds' plots and so forth, is when we see these images like that, the brightest part looks always as though it's exactly on that line that's coming across here, which is what it is in the image plane. But actually, if you look in the source flame, and if you were to look down on it, then this light path is coming from the back. So of course, this is just another effect of light bending around a very rapidly spinning black hole, that actually the material you're looking at is not where you think it is if you just look at it. An interesting thing about this whole thing is the absorption in a vertical sense on the disk corresponds to a column of 10 to the 23. The density of the disk is 10 to the 20. Okay, the density of the disk is 10 to the 20 per cubic centimeters. And so we're looking at not very much of this stuff. And the ionization parameter of the absorber is 10 to the 4. I've already mentioned that. The ionization parameter of the disk itself is 10. So this stuff is 1,000 times less dense than the disk. So therefore, its density is 10 to the 16. And this does not correspond to a very large depth. And the depth of the absorber is around 10 to the -4 gravitational radii. So this absorber is very thin. It's rather like the paint on the wall, where the wall itself is the disk, and we're looking at the paint on the wall. But you know that paint on a wall can change the nature of the wall, what it looks like, okay? So that's what's going on here. So maybe I'm wrong. Maybe there really is a massive outflow, and that would represent large amounts of matter coming out at a quarter of the speed of light. Or maybe all we're doing is looking at the surface of the disk. Further work on this is going to have to wait for new spectra, and CRISM, the Hitomi replacement mission that should happen in launch and be up there in 3 years' time, will be very interesting for this. And comparison with other UFO features in other objects. Further tests of the Lamppost model, I'm going to now just get to my very last new part, and that is testing the Lamppost model. We can actually make use of the measurements we're making now of the density of the reflector. The reason we can measure the density from the reflection spectrum is because free absorption is energy and density dependent and strongly affects the soft X-ray spectrum at high densities. The energy at which free opacity equals the Thomson opacity in an optical depth of 1, say, is the energy varies as √n. So as the density rises, so the free absorption becomes more important at higher energies. And these are some high density spectra that Javier Garcia made. And what we see is, I've shown you reflection spectra like this before. This is an EFE spectrum, and he's used a slightly different value of gamma and so forth. But essentially, as you wind the density of the disk up, so this part of the spectrum gets pushed to the right. Okay, so as we go up to 10 to the 19 density, then the spectrum falls over here. The peak of the spectrum's here, whereas down, the sort of, all of these are emission lines, but this is a bulk of it peaking there, the bulk of it peaking down there, and that is this √n effect as we're going up in density from 10 to the 15 to 10 to the 19. The fact that it's going like that means the whole spectrum gets squashed up, and since what goes in must come out in these reflection models, all the hard photons that go in, all that energy and power going into the slab has to also come out. It then gets squashed in, comes out down in the soft X-ray band. And in other words, the surface of the disk gets hotter. And this means that we've got a way of measuring the density of the disk, the density of the reflector. So these data, what you can see there is by fitting the spectrum, particularly if we got the soft X-ray spectrum, we can start to measure the density. And Jiachen Jan has been doing that with IRAS 13224. We got 5 different flux states. These are nu spectra or EFE spectra. And what you can see there, this lower curve is the reflection, the middle curve is the power law, and the total is there. And what Jiachen is showing here, and incidentally, he's put the absorber on both the reflection and the power law, is he's then comparing the total to the data, and we've got the ratio plots along like this. And what I think you can see is there's a pretty good fit for these, and the ionization parameter of the disk itself is 10. The density is around 10 to the 20. And the abundance of iron is 3. So I don't know if some people will remember early fits to this object and we were getting abundances of 20, and other such things, but no longer do we have that problem. Also, you can see from this plot here, the reflection is above here, the reflection is way above the power law, and when we go to when it's bright, the reflection is way below the power law. So that's what I meant in terms of the absorber. You know, this is reflection dominated at low flux and power law dominated at high flux. Well, let's not bother with these plots, which are just the reflection, flux, and so forth, and look at this plot here. What Jiachen has done is to take the ionization parameter and use the equation xi is L over n r squared, or h squared, that's the height of the corona. We know n, we know n, we know L because we can measure the luminosity of the corona, and we know xi, so we can work out what we call a Euclidean coronal height, h naught, and it varies between 0.5 and 1. And if you remember back to Will Alston's reverberation heights, his reverberation heights were between about 5 and 12. So this is not very good agreement, but we need to include the effects of strong gravity because we need to work out what the ionization is in the inner parts of the disk below the corona. There's then very strong light bending, which will pull the radiation from the corona down. The radiation from the corona gets bent down onto the disk. Also, what happens is because you're below the corona, the light, as it were, falls down onto the surface of the disk, and so is blue shifted in the rest frame of the disk. And all of those effects combine together in work that Thomas Dowser has led to give a very strong flux boost. And that can be between 100, if you're at 2 gravitational radii, about a factor of 10 at 5 gravitational radii, and a factor of 2 or 3 at 10 gravitational radii. You can then use this boost factor to convert from the Euclidean height to the actual height, which I've drawn over here. And the actual observed values are sort of there. And what we convert them to is between 2 and 4 to 5. So we're almost there. The coronal height measurements are from the Euclidean estimate is 0.4 to 1.7. When you boost them, they go to 2 to 5. Reverberation gives 5 or 6 to 12. So we're almost there. Now, other considerations which we've not actually done yet is think about returning radiation. That is when you have the corona here, it goes and irradiates this part of the disk, giving rise to what we call primary reflection, but some of the reflection will go across and hit the other side of the disk, and that's secondary reflection. That's returning radiation. It goes from the disk and returns to the disk. And that was considered by Cunningham back in the 1970s. But there's recent work by Dan Wilkins, who had a paper out just a couple of weeks ago. Another issue to bear in mind is we're assuming in these calculations that the corona is a point source, which is silly, isn't it? And it must have some finite size. And the top of the corona is probably going to be controlling the reverberation results, and the bottom of the corona, or the bottom of the corona, is going to control the ionization results. And so the difference between these may be telling us something about the size of the corona. We've got to work that through. I won't spend a long time on this plot. Those of you can ask me questions about this plot, but we're using modified Shikura-Sunyaev equations according to Svensson and Zyarsky's paper in '93, and they talk about the density of the disk, and in a radiation pressure dominated disk, they have the same density with height. So measuring the density at the surface, you're measuring the density of the disk. And this is what Jia Chen's found for a bunch of AGN down here, and IRAS 13224 is this blue bar up here. And the implication of what's going on here is that most of the power of the disk, most of the gravitational energy released from the disk is appearing in the corona. So the magnetic fields are transporting the energy out to the corona extremely efficiently. So this is something new, I think, that we have to start considering. So now for my summary slides. Relativistic reflection and reverberation are common in luminous accreting black holes. The first X-ray reverberation mass was made early this year with a 10% uncertainty. There's possible absorption lines from the disk surface. And the surface density of the objects of AGN, provided the black hole mass is less than 2 × 10⁷ solar masses, we can start to do that. And we can do it routinely with black hole binaries as well. There's approximate agreement between the height as measured by reverberation and also through the ionization parameter. And we're obtaining the geometry of the innermost 5 gravitational radii around black holes. We're actually measuring the details of what's going on in the heart of this AGN. Last slide. There are dozens of bright AGN which could be observed to this depth with long exposures. So XMM, please give us lots of time. If we get EXTP, Athena, and Lynx, there's going to be much more of this kind of work being done. The high density reflection models open a new observational approach to accretion disks. We can start to see what's going on in the centers of these objects. Since black hole binary disks, by the way, are more ionized, then surface absorption is unlikely to be observable. And where people have seen absorption lines in black hole binaries, it's very likely that's for real. If they see outflows, John Miller's done a lot of this work, then it's going to be an outflow. And we need to revise accretion disk models to account for powerful coronae. Now, Ramesh Narayan and his colleagues have done lots of work on getting powerful jets out of these with MAD disks. Let's see what happens when you try and make a powerful corona. And if you've got a powerful corona, there are implications for super Eddington behavior. And I'll finish there. Thanks for listening.
Thank you very much, Andy. Of course, we don't get to do a proper applause, but I'll just...
Thank you, Belinda.
Really beautiful data there. So my job now is to go to the Q&A and pass on some questions from your audience. There's some people with very complicated names here. The first one is from Razia Amami. I'm sure I'm not pronouncing that correctly. And they ask, how does the X-ray reverberation vary for the case of tilted and precessing accretion disks for the reflected light?
Yes, very interesting if the disks are precessing and doing all that kind of thing. So far, I don't believe anybody's yet measured reverberation from precessing disks. It will be interesting when it happens. I don't think that is happening in IRAS 13224, but undoubtedly there are objects where that's happening.
Thank you. Randall Smith would like to answer this question live. you want to go ahead, Randall?
Oh, sorry, no, I was just cleaning up the questions. Keep reading.
I thought you were going to give us the life, the universe, and everything answer. Okay, the next one is from Laura Brenneman, whose name I can pronounce, at least I think. Hi, Andy. Thanks for the fascinating talk and congratulations on the much-deserved Kavli Prize. Question, what types of observations and analysis, for example, with CRISM and NuSTAR, will allow us to differentiate between UFOs as massive outflows versus absorption within the disk, as you suggest?
Well, I think, and by the way, hello, Laura, thanks for the question. What CRISM can do, I would hope, is to actually reveal much more in the way of structure in these particular absorption features. And if, for example, there are multiple absorption lines that don't fit into a simple spectrum, that iron K alpha, K beta, and so forth, and also the absorption lines, then I think that would be a way of ruling out what I've been talking about. But, and I know multiple lines are seen in some objects, but I think so far they don't yet rule out what I was talking about. But so that's the kind of approach I'm going to think about taking.
Can I follow up on that? Wouldn't you end up with both? You could have an outflow and also be seeing the accretion disk, right?
Indeed, and yeah, sure we can. And I also didn't mention, of course, that if any quasar experts out there, then there are, of course, broad absorption lines in the UV and optical from quasars, or some quasars, which show velocities of tens of thousands of kilometers per second. But as far as I understand, those are at significant radii from the disk, significant distance from the black hole. These would actually, what people think with regard to UFOs is if they're outflows, then they are at tens to hundreds of gravitational radii. The whole action is happening very close to the black hole. And, very exciting if so, but I think we need to really check out what is happening in detail.
Thank you. So the next question is from Ramesh Narayan. Do you understand the physical reason for the extraordinary X-ray variability of this source? Is the object in a special accretion state, or are we viewing it at a special angle?
Thanks for the question, Ramesh. I don't know is the blunt answer. As you know, accretion tends to be very variable. One issue about accretion disks, of course, is the standard Shukurov-Sunyaev disk. The equation of the time dependence in the disk is a diffusion equation, and diffusion tends to smooth everything out. So it's actually surprising in a way that things are so variable. And I think when it's like that, it probably is pointing to magnetic fields. And so there's something going on here. And in terms of what the variability in this object is, I think it is a combination of intrinsic variability and also the corona going up and down, because when the corona is at a low height, because of gravitational light bending and redshifting and so forth, then it will appear dimmer than if it's at a greater height. And so we've got two kinds of variability here, which I think we see hints of in terms of the RMS flux and so forth. And for some reason, this is jumping up and down. Now, I've read some of your papers, Ramesh, and it looks to me like if you have strong magnetic fields in disks, you're going to end up with large variability. I don't know what you think about it. Also, I would add, if I may, just, and that is, jets are often highly variable, and maybe these coronae are, somewhat related to jets.
Okay, thank you, Andy. So the next question is from, and I won't pronounce this correctly, Agniva Roy Chowdhury, who says, hi.
Hello.
This is a long question, so please bear with me. Did you cross-check your time lag magnitudes from discrete correlation or something similar? Won't phase spectrum time lags have different magnitudes due to the effects of binning? Also, since the method has phase flipping, is there a way you could separate false lags due to that from actual real lags? Thanks.
Okay. In terms of correlations, I'm not sure I'm understanding quite what you're saying. All I would say is that Abdu Zogby, who was a student of mine working on the 1H0707 data, he actually analyzed the data in a paper in 2010, not using a Fourier approach, but using a cross-correlation approach. And if you look in the paper there, you can actually, I could have included a plot from that. You can actually see, if you smooth the data, you see one effect. If you take out the high frequencies, you get one scaling between the light curves. And if you smooth, if you concentrate on the high frequencies, you can see the time lags. You can see that the reflection part, dominated part, is lagging behind the power law dominated part. So all of that hangs together from that other approach. I don't know if that's what you were asking. But in terms of phase flipping and so forth, which is an issue in these in this kind of analysis, that is, I believe, accounted for within the Mikhail Dovshak's models.
Okay, and he had another, he or she, don't know which, had another question. Has there been a direct comparison between the X-ray reverberation measured mass with that from optical reverberation for any source?
No, the only X-ray mass is the one for IRAS 13224. Will is working on others, but in terms of other measurements of the mass of IRAS 13224, they range between 5 times 10 to the 5 and several times 10 to the 6, based upon all the scaling methods that people do, which are calibrated by optical reverberation masses, but there's been no definite, been no campaign on this object, and I'm struggling to think of any optical reverberation masses of narrowband Seyfert ones, but maybe somebody will point out there is some.
Okay, that's it for the questions and answers that are in the Q&A. So I think that comes to the end of the proceedings. So I'd definitely like to thank you, Andy, for taking the time, particularly late in the evening, to share with us the story of this very interesting object. And thank you on behalf of all of us. Charles, would you like to say something else? You've unmuted.
I was just unmuting so I could clap. Thank you very much. This has actually been a great way to start our first ever Zoom series of CfA Colloquia.
Yeah, it's for me, it's also strange because of the fact that I can't see the audience.
Yes.
That's always important. It's sort of whether people have dozed off or whether they're really following what I'm saying.
Well, I know I did not doze off for a second.
No, I can vouch for that, and neither did I.
Yeah.
Thank you.
Thank you very much.